in presence. In fact, this is the first workshop we are organizing after the virus started. And in fact, the idea was that we stopped all the activity in presence and including seminars, of course. So we decided in our department to organize a few workshops to restart to use the source that we have to organize at least online workshops. And but we didn't expect so much success. There are a lot of participants, around 140. So it's which is one of the positive things, the positive side of going online. But while we hope very much to be to meet in presence, at least we take the advantage now that we can easily meet virtually. And the chosen subject is Entropy and QFT. The entropy is well-known subject, of course, and quantum field theory is also a well-known subject, but only recently a lot of activity started in the relation of the two, in the sense that what we may call, let's say, quantum information for quantum system with infinitely many degrees of freedoms. I think there are a lot of perspective, a lot of things that we can do, and we experts in quantum field theory, especially from the algebraic viewpoint, I think we have the tool that others don't have to make the bridge to analyze the entropy of quantum field theory. So this was a very, very simple workshop, just intended to gather a few of us and to start a collaboration, at least from the point of view of talks. So I think the next talk is in about 10 minutes, and it will be in about 5 minutes, but we may start even a couple of minutes earlier if you want. All the talks are registered and will be posted in the YouTube channel of our university, at least the talks that speakers agree. And the first speaker is Stefan Hollands from Leipzig University, that we all know very well. And the title of his talk is State Recovery. So I think if Stefan is able to share the screen and prepare, we can use a couple of minutes to prepare the screen, and then we may start as soon as you want.
Inviting me and for organizing this nice get-together with a well-chosen theme from my viewpoint at least, and also thanks to Fabio Ciolli, Vincenzo Morinelli and Giuseppe Ruzzi for co-organizing it. My talk is about state recovery, a program which is very well investigated in the quantum information theory literature, and which has very close connections to ideas about entropy, and of late also has a close connection to some constructions in quantum field theory, as I hope to be able to show you. Right, so let me get into some definitions just to set the scene. So we decide that according to the algebraic approach and the approach common in quantum information theory, that observables associated with a system are members of an algebra of operators, which is called A or B or C, etc. And it's those observables that are accessible to someone with access to with it being able to manipulate the system. So this talk, A, B, etc., will always be for Neumann algebras, which are algebras of bounded operators that are closed under the star operation and under weak limits. States are positive normal linear functionals on such an algebra. So they take an element and give a number, which is interpreted as the expectation value, and to have a probability interpretation, it's agreed that the value on the identity operator is 1. Now, central to this talk is the idea of a quantum channel. A quantum channel is mathematically a linear map between two operator algebras, which maps a positive element to a positive element, and in fact, is completely positive. It is a requirement that is still positive if one takes a tensor power of both algebras with a finite dimensional matrix algebra. Now, physically, channels are widely agreed to represent the most general quantum operation in physics. So that could include a quantum error correcting codes. A channel could represent transmission through a noisy transmission. It could represent the operation of restricting to a certain subsystem. It could implement a projective measurement. It could time evolution in open quantum systems or closed quantum systems, for that matter, are all examples of channels. And as I said, a channel is the most general, or is thought to be the most general operation that you can perform on a physical quantum system. Now, states are particular examples of channels where one algebra is just the algebra of complex numbers. I always think of channels as acting on observables. So this is kind of like the Heisenberg picture, where in the example of a time evolution, which is a channel, you think of the observables as evolving with time, but as usual by duality, you can also think of a channel as acting on a state, whereby now just the action is given by concatenating the action of the state and of the channel. And that is the kind of more conventional viewpoint taken in the quantum information literature. But as usual, as the Schrödinger and Heisenberg pictures are completely equivalent, then so are these. So you can, in just the same way, you can think of channels acting on states or on observables. Now, states, the channels typically cannot be inverted. I think there's some noise in the background. Okay, I think it's gone now. So the important point is that channels cannot typically be inverted. So the unitary time evolution is not a good example of this phenomenon, because you can, at least in principle, run it backwards. But a projective measurement, for example, where you project the state onto an eigenstate of the measured observable, that is a typical example of a non-invertible channel. If you have noisy transmission, then the fact that it's noisy means you cannot completely recuperate the information being transmitted, quantum error correction, and so on and so forth. So channels, or if you have an open quantum system, there is transfer of information out from the system. So it is quite clear that channels typically cannot be inverted. So the question of this talk is, under what circumstances can a channel be nearly inverted? So can you, after having transmitted a message through a noisy channel, can you nearly reconstruct the message? Or under what circumstances? And the focus here will be channels of general sigma finite von Neumann algebras, where the algebras are not necessarily of the type 1, I say what the type 1 is. And the motivation is very clearly the application of this kind of idea or the inequalities that we get to quantum field theory and also to a certain degree holography. Okay, so let me introduce some tools known to the expert, but perhaps not known to the non-expert in operator algebras. So von Neumann algebra is said to be in standard form if it acts on a Hilbert space and there is some object called a natural cone and a modular conjugation. I'll explain in just a simple example what this is concretely. But then if you have two vectors, you can define.
Maybe I can see that. I can always see the same slide. Can are you changing? I'm still on channels. Slides on channel probably. I don't know if it's a common problem also for other.
Yes.
Can you see my entire
This is a
screen
common
now?
problem.
Okay. Okay.
Is a common problem?
It's a common problem. Yes.
Okay, let me share again.
Thank you.
So can you see my slides now? Can you see my screen?
No.
No.
Mm-hmm. Okay, I think I need to maybe log on again. I don't think there's another way.
No way.
Okay, can you hear me?
Yes.
Okay. Can you let me share my screen again?
You probably already you cannot do this?
No.
So let me just a minute. Okay. Sorry, just a sec. Okay, here.
I also have a lot of echo in the line right now.
So now you should be able to share. Am I right? Okay.
So you should see a slide called "This Talk" now.
Yes.
All right, I'll try to continue.
Thank you.
So you have to let me know if this gets stalled again.
Okay. Okay.
So my question was, under what circumstances a channel can be nearly inverted? And my focus is on channels of general von Neumann algebras. I'm starting to introduce some basic tools. The basic tool that we'll focus on is the so-called modular operator. It can be defined for general von Neumann algebra, and this was supposed to be on this slide, but because I'm losing time, I go straight to the example where the algebra is of type 1. Can you see the slide type 1?
Yes, we can.
Okay, so this concerns the special case where the algebra is just the set of all bounded operators on a separable Hilbert space, H. The inner product is the Hilbert-Schmidt inner product, with H being the Hilbert-Schmidt operators. The algebra acts by left multiplication, as in 3. State functionals are density matrices, as in 4. One has a natural purification of a state, which is just the square root of the density matrix. So the square root of a density matrix gives a vector, and the expectation of value of this vector of an observable is the same as 4. Let's ignore 6 and let's look right at 7, the modular operator. It takes a vector and then it multiplies with one density matrix to the 1/2 from the left and another density matrix to the inverse 1/2 from the right. This operator is called the modular operator or relative modular operator, and it can be defined also for general von Neumann algebras. Now, there's a condition that a state is called cyclic and separating if the purification is an invertible Hilbert-Schmidt operator. Now, the notation I'm going to use is that when A is of type 1, then a state is a density matrix. A density matrix has a square root, or written as eta, eta star. And then the expectation value is the Hilbert-Schmidt inner product of eta with A eta, which is also the usual trace of A eta, eta star. Now, the advantage of this relative modular operator is that you can define many things with it in the general setting that have a very natural and simple expression in the setting of type 1. So an example is the so-called relative entropy. The relative entropy is a measure of the distinguishability of two density matrices in the type 1 setting, and it's given by minus the von Neumann algebra and entropy of the state plus this or minus this second expression. And in terms of modular operators, it's nicely written is just this one expression, which is defined generally. It is a measure of the distinguishability, and in fact, it means the average information gained if we thought the state was eta, but now we learn its size. So that's the operational meaning. And in general, eta, the second state, is thought of as a reference. So you should see next the slide, data processing inequality.
Yes.
Mm-hmm. Okay, so now we connect the relative entropy with the notion of a channel introduced before. If you have a channel, you can apply it to a state omega psi and to a state omega eta to get a new state or new pair of states. And the key statement is that the distinguishability between these two states always goes down, in the sense that one has this famous data processing inequality DPI. It was proven by various people in at various levels of generality. The most general or final version is by Uhrmann from the 70s. It is So it's a property, this data processing inequality, that is shared by many similar distinguishability measures. It's absolutely key for entanglement quantification. It implies many classical properties of the von Neumann entropy in the type 1 case, such as convexity and strong subadditivity. And it's interesting to study the case where you have equality without the state, the channel being the identity. And this case was studied by Petz and others in the 80s. We'll come back to this. So proofs of this inequality, there are different ones. Some use subharmonic analysis, which is a strategy originally used by Lieb in his Lieb and Muskai in a proof, and which is underlying much of Araki's theory, and it's been also used by Epstein and others in this kind of context. Another route is via variational principles, and this also goes back to Ullmann, Kozaki also, and many other people. Okay, so now we come back to the question of this talk. Under what conditions can a channel between two observable algebras be approximately inverted? So what I mean by this is that there should exist another channel going the other way around, called R for recovery, such that the original state and the state passed through the channel T and afterwards through the channel R are close for a class of state. And that class could depend on the class of channels that you want to consider. So if this happens, then the idea is that you shouldn't lose too much information by applying T, or vice versa. You can only have this if you don't lose too much information by passing a state to the channel T. And so what not lose too much information means is that the difference between the S of the states and the states passed through the channel, the thing that's non-negative according to the data processing inequality, should be in fact small, like epsilon. So in fact, if you have exactly 0, so you have saturation of the data processing inequality, then you would expect that you have perfect recoverability of the state, in the sense that you while not being able to invert T, you can recover the state in the sense that you have this equality. So the idea of a recovering channel is crucial to very many questions in quantum information theory, and therefore the question as to how well a recovery channel can recover the state is of really fundamental importance for many areas or many classes of questions in quantum information theory. So there is a particular recovery channel given already in the 80s by Petz, and is therefore called the Petz adjoint of the original channel. And well, you can find its definition, for instance, in the text by Petz and O'Hare, but it goes back to Petz papers in the 80s, and Roberto Longo has a nice description of this Petz adjoint in terms of bimodule, which however not I'm using, but there is a connection to bimodules underlying many things I'm saying. So it's defined as follows. So remember that a channel acts between algebras. So if you want to define an adjoint, you should have an inner product on the algebras. And the natural inner product to define is what I call the KMS inner product. So I think it's defined in terms of the modular operator, but maybe it's best to just look at the expression in the type 1 case, where eta is the square root of a reference state. So in the language of Hilbert-Schmidt operators, it's the purification of the density matrix. It's the square root of the density matrix. So this gives an inner product on the algebra A, and if you have a state on A, you get via T a state on B, and then you also get by the same formula an inner product on B. And now if you have a state, a channel from B to A, you can define its adjoint, having now these two inner products, and that's called the Petz adjoint. And it maybe look a little unnatural to use the KMS product if you don't know, if you're not in the business. But for example, one nice thing that happens is that this adjoint of a channel is now also a channel. So it's completely positive. Now, what one uses in the following theorems is not quite the Petz channel, which it would be nice to have it, but one uses a slightly different channel called the rotated Petz channel or Petz map. So in the algebra A, or the Hilbert space of A and of B, you have the so-called modular flows, which is in some sense the Heisenberg time evolution defined by the logarithm of the density matrix for eta B in the time 1 setting, and it's similar for A, but it's defined for general von Neumann algebras via the concept of modular operator. So this again is a channel, but it involves additionally these time evolution, or you could, that's why they're called rotated. It's not really a rotated, it's maybe time evolved. Petz channel would be a better expression. Okay, so what are some results? So these go under the name of improved data processing inequalities. So as I've mentioned, Petz et al. Study the case of equality, so no information lost after applying the channel. Then he shows that the Petz adjoint is a perfect recovery channel. And quite a while later, there was an important paper by Roma, Farsi, and Renner in 2015, who basically investigated the case not of equality, but of approximate equality. Now, I don't want to go into precise detail what the result was, but that was roughly their setting. This paper has triggered quite a few improvements, variations by different subsets of people, different permutations of people. I mention here a few in the references. We will consider a particular improvement of this inequality that I'll show in a theorem explicitly. But I should point out that almost all of these results have been restricted to type 1 von Neumann algebras, and their proofs are also very obviously restricted to this case, I would say. And without either a very sophisticated approximation argument or a kind of an argument of a more intrinsic argument using intrinsic tools of von Neumann algebras, I don't think a generalization of type 1 to arbitrary von Neumann algebras was possible. We did obtain such a generalization in a recent work with Tom Faulkner, Brian Swingle, and Yi-Su Wang, and also Faulkner and myself. Junge and Laracuente obtained also generalizations, which I believe to be at least morally very similar, but they used, I would say, a quite different technical set of tools. Well, we're all using heavily the concept of an LP space of operator algebra, but there are many versions of this which look quite different And it seems we use a rather different version than them. So now you should see main theorems. Can you see the slide main theorems?
Yes.
Yes, we can.
Okay, and do you have no echo in my voice?
No.
Okay, good. I have a lot of echo feedback, but that's okay. So what are the main theorems? Now, the first one was obtained in this paper, this joint paper with Faulkner, Zwingle, and Wang, and the generalization of that result as presented here is in a separate paper by Faulkner and myself. Now, we have two von Neumann algebras, B and A, sigma finite, but otherwise general. We consider the difference appearing in the data processing inequality, which we know to be non-negative. But the improvement is that we have an explicit lower bound, which despite the apparent minus sign is also non-negative. And it involves the so-called fidelity. It involves the original channel. It involves the rotated recovery channel. And it involves a particular probability density given explicit by this expression pi over cos 2 pi t plus 1. Now, you should read this inequality as follows. Suppose the information loss is small, let's say epsilon. Then the left side is epsilon. So the right side is bounded by epsilon. And so you get a bound on the fidelity. So the log of the fidelity wants to be 0. So the fidelity wants to be about approximately 1. So it means I recover the state omega psi from its version passed through a channel, which is omega psi convolved with t, by recovery map with high fidelity. So this is what's written here. A small information loss in the data processing inequality implies proximity of the original state and the recovered state to high fidelity. So there was a previous version of this result applicable to type 1 von Neumann algebras that appeared in 2018 due to Junge, Renner, Sutter, Wild, and Winter. And our result can be seen as a generalization to general von Neumann algebras. The fidelity explicitity in the type 1 setting, this particular expression involving square roots of density matrices. So it generalizes the amplitude, the transition amplitude for pure states. You can think about it this way. Note that you can pull the integral inside the fidelity because the fidelity has, or minus the fidelity, has appropriate convexity properties, and so you can use a version of Jensen inequality, so thereby obtaining a weaker inequality. Here is a second theorem. It has a similar spirit, but looks different. So again, we have the difference appearing in the data processing inequality, which we know by that inequality to be non-negative. But now we have an explicit lower bound, and now involving the so-called measured relative entropy. The measured relative entropy is the supremum of the restriction of the relative entropy to an arbitrary commutative subalgebra. And the terminology measured arises because usually think of this algebra as generated by the spectral projections of some observables. So you measure an observable, and the statistics of the measurement outcome are then used to determine the measured relative entropy as the classical relative entropy defined according to the relative probability of occurrence of a measurement value. But mathematically, it's just with this. And R is a channel which is basically the rotated recovery channel, but now you average this against this external probability distribution beta 0. So this gives another channel. So again, a small information loss in the data processing inequality. So if the left side is epsilon, now implies the proximity of the state and the recovered state, but now with respect to the measured relative entropy. And this result generalizes another paper from the quantum information theory community cited here to general von Neumann algebras. The integral here cannot be pulled out of the integral. And so it's not quite clear which of the two inequalities is sharper, whether the one from theorem 1 or theorem 2. It can be one or the other depending on the case. But in the classical case, when the density matrices commute, then it's this second theorem gives the sharp result. So now you should see a slide called half-sided modular inclusions.
Yes.
Yes. Okay, so the rest of the talk is an application of these theorems to a situation in quantum field theory. I think rather than going through the formulas, I give the picture. So you have two operator algebras associated with wedges in quantum field theory, and one wedge is sitting inside the other, like so. Then you have an operator algebra AA as shown above. The channel in question is the inclusion channel of AA into the big algebra defined by the entire wedge. And under this circumstance, you can show that you automatically have a representation of translations of the light ray or the wedge by the Bx plus A group, and the translations in particular along the X plus axis, which are labeled by the translation vector null vector A, are generated by a positive non-negative linear operator T, called usually the NEC operator. Okay, now you can work, this is an example of the setup with the channel being just the inclusion channel. And you can compute the various objects, and the end result is corollary here, which gives a lower bound on how much the relative entropy decreases as you as you increase A. So by restricting the algebra further and further, so making A bigger and bigger, the states become less and less distinguishable because you have fewer and fewer observables. And this inequality quantifies by how much they become less distinguishable. Again, it involves the fidelity, but now also it involves the exponential of the ANEC operator. So here is a conjecture. So one may in particular take A to 0, and then the inequality there would be an inequality greater than or equal, but there's a conjecture by us that you get an equality in this case. So it becomes sharp in this case. And if this were the case, you would get a proof of the so-called QNEC, because you can now apply this inequality to replacing A by a shifted algebra and use the monotonicity of Ebb. So you'd get the QNEC, which broadly speaking is this convexity property. Okay, so what are the tools? Maybe 3 minutes for my tools. Yeah, so I have until what? How many more minutes? 3 minutes, is that right? Okay, I assume 3 minutes.
I think you start that you should have 45 minutes, so you start that 10 until 55, so until 5:23.
Until 55.
Yes.
So 10 minutes. Okay,
Yes.
good. That's fine. But, so some tools to prove these results. So again, what are the results? Theorem 2 gives a lower bound with the measured entropy. Theorem 1 with the fidelity. Okay, so you may know for Hilbert-Schmidt operators the usual LP norms, which are defined by taking a matrix zeta, forming its pth power, and then taking a trace and taking the pth root. These are very well known norms in analysis. You can give what is called a non-commutative generalization, where you stick between zeta and zeta star a density matrix of some reference state raised to a certain power, also involving P. So these are the so-called non-commutative LP norms. The terminology non-commutative arising from the fact that in the usual case, you can write it as an ordinary LP norm just of the eigenvalues of zeta, which you cannot do in the second case if C doesn't compute with zeta. Right, so this form is not very useful for a general von Neumann algebra because you don't have a trace, but you can give a variational definition involving the modular operator found along many profound and technically hard theorems about these norms in the paper by Araki and Masuda. So I'm not going to show why this variational definition is equivalent, but it's for matrices, it's a very simple calculation with Lagrange multipliers. So some special cases, P equal to 2 is just the operator, is just the Hilbert space norm. So recall that in the type 1 case, the Hilbert space was itself the space of Hilbert-Schmidt operators. So it's the Hilbert space norm and on the space where the von Neumann algebra acts. The one norm is the fidelity. So you start seeing perhaps a connection with the theorem. The infinity norm is related to the operator norm as such. And the limit as p goes to 2 is related to the relative entropy. So the idea pretty much is that the p norms interpolate between the fidelity, the relative entropy, and the ordinary Hilbert space norm. But that's certainly not all there is to it. A very important lemma is a kind of interpolation result. So such results are quite important and widely known in analysis, also in commutative LP spaces, where there are classical results. So if you have some h-valued holomorphic function in a strip, then you can estimate the LP theta norm, where p theta somehow is inside the strip, by the p norms corresponding to the boundary of the strip. And in this interpolation theorem, these probability distributions alpha and beta appear, and the theorem is proven in the classical case using a lemma called the Hirschman interpolation theorem, or the Hirschman, which is basically a version of the Poisson kernel. And in the non-commutative case, especially non-commuted in von Neumann algebra case, one has to use really profound results by Araki and Masuda. Okay, so how to relate this to our theorem? So the key trick is to define a suitable analytic vector. And the analytic vector is defined, first of all, you have to bring in the channel. The channel has not entered yet. So you have a state psi, then this induces a state psi on A and B via the channel. And then if psi is cyclic and separating, you can define this operator V. So it operates between the Hilbert spaces K and H, where the operator algebras B and A live. And then the properties of T show that this V is a contraction. And that in turn can be used to verify that this vector G is analytic suitable. And to this vector, one applies the interpolation theorem. I assume you can see the slide tools interpolation.
No, commutative interpolation.
Yes, thank you.
The
Okay.
tools interpolation, yes.
Okay, so you apply this theorem, and then somehow the entropy difference pops up, the Petz recovery map pops up, the rotated Petz recovery map pops up, and the fidelity pops up, and this probability distribution beta 0 pops up. So this works very nicely. Okay, still not good enough, because one wants to take a certain limit of the norms as p goes to 2. And it turns out that for general von Neumann algebras, this limit is extremely subtle. And the resolution that we found was to define certain regularized vectors first, with using functions with certain analyticity properties. And then, so the key problem is, usually if you approximate a state, then this doesn't mean that the entropy is approximated, because the entropy is not a continuous functional of the states. And this, if you don't use an approximation tailored to the problem, you have no chance to give proofs. And so this is a kind of approximation tailored to the problem, which we found after a while, and it gives a very nice kind of upper semi-continuity of the relative entropy, with a correcting piece involving terms that can be made quite small using a sharp Hausdorff-Young inequality. Further inequalities needed are the Araki-Lieb-Tiering inequality, which is roughly the one written here, and various applications of the Harnack inequality for harmonic functions. And for theorem 2, one uses, in fact, the Hirschman dilemma with a large value of P0, and then one also needs a version of the Lee-Trotter formula and very heavy use of Araki-Masuda results. Okay, now having gone through some of the technical hurdles that one has to face proving this theorem, I still think it is a very nice and to me fundamental looking result. It is an improved data processing inequality, where you say you when you apply a channel, you don't just lose distinguishability of the two states, but you can say or give an estimate how much you lose. And that implies an approximate recovery when the loss in the data processing inequality is small. I believe that these inequalities can be viewed as rather non-trivial inequalities for general von Neumann algebras. And there's a very intimate and in fact improvement of the quantum null energy condition when one applies this setup to inclusion of wedges. And with this, I would like to end my talk.
Thank you, Stefan. Very nice talk. So if there are any questions, please ask questions. So I see one question by Jan Mandrisch.
Hello, thanks for the nice talk. I just wanted to ask if the beta zero, so the form of the beta zero, this weight function or probability distribution, if it plays a special role, or is it so? Is it a choice that you make, or yes? That would be my question.
Can you still see my screen?
Yeah.
Okay, maybe I'll go into this. Yeah. So this kind of expression down here, it comes out of this interpolation theorem, and indirectly it comes out of the theory of harmonic functions on a disk. So if you have a harmonic function on a disk, then somehow you can express the interior values by the values on the boundary by Green's theorem. And if you map the disk conformally to a strip, somehow these Jacobians pop up out. Why they are, and so this is somehow intrinsic to the setup of strips and disks in the complex plane and subharmonic analysis.
Okay, Rainer Vergata, do you want to ask anything? Rainer, you raised your hands, huh?
I think, Rainer, your microphone is open, so you can just talk.
No, maybe it's a mistake, I don't know. Is there anybody who wants to ask questions? Bernard K.
Okay, a very quick and maybe stupid question, but I was just wondering, this term with the cosh, what was it, 2 pi t or something, has that got some physical interpretation in terms of a temperature or something like that?
That's a good question. Yeah, so as you know, Bernard, in this very general setting, you can normalize the temperature always to 1. But in a more physical setting, you have an external idea what the temperature is, like in black holes case. Mm-hmm. And I believe if you were to normalize the parameters according to this physical temperature, then indeed it would be the Hawking temperature would come in the usual way that you always have in these Koch factors or Tanch factors.
Okay.
Bernard, Stefan, what about the classical case? Are these inequality new or well known?
Yeah, that's a very good question. I have people here that are big experts in partial differential equations, and it seems at least theorem 2 is not totally trivial even in the classical case. Theorem 1, I think, depends what you mean by the classical case. So depends what channel you want to consider. So the typical case is if you have a a dissipative semigroup. So you get a one parameter family of channels. And then you get certain inequalities, which I think are not known in all cases, even in the classical case.
Good. Is there any further question?
So maybe I try again. Can you hear me?
Yes.
Okay, now you can hear me, right? Okay,
Right.
Stefan, maybe you can go back to, I think it was the last slide.
Conclusions?
Yeah, or one before, I guess. One before. I mean, these quantities that you're working with, do they have any relation to these entanglement measures that have been investigated for quantum field theory, like by Summers and Werner? Do you see any relation?
Okay, so there is a very well known way to build an entanglement measure for any divergence which satisfies the data processing inequality. So you consider the difference between your given state and the space of separable states. And then depending on what you choose, so S, relative entropy, is a choice. You can take the max entropy. There's a big zoo of various divergences. And for each one of these, you get an entanglement measure. Now,
Yes.
the one by Werner and Summers is the Bell measure, and I'm not sure whether it can be built this way. But I think it's nowadays considered, while it's very nice and physically intuitive, it's not a very strong indicator of entanglement. I mean, it is an indicator, but you can have, as you know, entangled states where you have no violation of Bell inequality.
Yes, yes.
And so the motivation behind many of these generalized entanglement measures is to improve this kind of awkward situation.
Okay. Okay, thank you.
Good. Any more question? If not, we thanks again Stefan for this beautiful talks, and we resume in 7-8 minutes with the next speaker, Chris Fuster.
Okay.